So the top 4/5 or whatever of this worksheet gives you explanation how to write these half reactions. I want to do that with you on a new problem. So if I look at number 1 at the bottom of the sheet, it says aluminum metal displaces iron 2-phosphate in a single displacement reaction. The first bullet point says write the skeleton equation. Here's aluminum. It was iron 2-phosphate, so Fe3 PO4 2. It's a single displacement. The aluminum and the iron are going to trade places. That means I'm going to get iron and aluminum phosphate as my products. Now the term skeleton equation on the bottom of the sheet is referring to, don't worry about phase notations for this necessarily. Don't worry about balancing the equation, because when we're identifying what was oxidized and what was reduced, we don't need coefficients in order to do that. But what we do need to do in order to identify what was oxidized and what was reduced is we have to assign oxidation numbers. And that's what the last bullet point on this front side says. So remember, elements that stand alone, like aluminum and iron, are a 0. I'm not going to even worry about the PO4, the phosphate, because phosphate is the same on both sides of the equation. It's going to be a spectator ion. Again, get used to seeing that and then saving yourself a little bit of time. If this was called iron 2-phosphate, that means that the iron is a +2 here, and the aluminum on this side would be a +3. So far, that's more or less what we covered last class period. We okay with that? All right, so if you flip to the back side, the new thing says write the half reaction for that element that was reduced. Well, let's just start off with identifying what was reduced. Remember, how we do that is look at the oxidation number start to finish. Whichever element had its oxidation number go down, it was reduced. So in this case, what was reduced? The iron +2, right? A half reaction starts off with writing down what was reduced. To be reduced means you gained electrons. Remember, Leo goes Ger, gain electrons reduced. Now, I'll figure out how many electrons are in a little bit, but again, E with a negative sign is your symbol for an electron. And what did it turn into? It turned into iron 0. In order for iron +2 to turn into iron 0, how many electrons did it gain? 2. That's the reduction equation. Next bullet point down says write the half reaction for the element that was oxidized. Well, the aluminum had its oxidation number increased, so it was the thing that was oxidized. Aluminum starts as a 0. If you're oxidized, you lose electrons. Again, Leo goes Ger, lose electrons oxidized. So aluminum is going to turn into aluminum +3 plus a certain number of electrons. How many electrons would that be? 3. The charges on the left and the right-hand side of a reaction have to balance out. So aluminum neutral here, a +3 and a -3 makes that 0. A +2 and 2 negatives makes that 0 there. You may not have to balance the 0 each time, but the left and right side of the arrow should balance out. Speaking of balancing out, what I told you last time about redox reactions is something is going to be gaining, something is going to be losing, because you have to have kind of a conservation of mass idea that the number of electrons gained and lost are equal. That's not what we see right now up on the board. What we see is iron gaining 2 electrons and aluminum losing 3. That doesn't balance, which is why we have another bullet point that says write the balanced equation so that the electrons lost equals the electrons gained. What I mean by that is we might have to put coefficients in front of things in order to show that it's more than one of them reacting at a time. Just like a balanced equation has coefficients to show more than one's reacting at a time in order to get the right ratio. The way to figure out the ratio here is to multiply either or both the oxidation and the reduction half reaction by numbers that will allow the electrons gained and the electrons lost to balance out. So in this particular problem, I would multiply my reduction equation by 2. I'm sorry, 3. Ooh. I'd multiply my oxidation by 2. Because then I'd have 6 electrons gained, 6 electrons lost. Those would balance out. So when that third bullet point says write a balanced equation so that the electrons lost equals electrons gained, if I multiply this by 3, that'd make that a 3, that a 6, that a 3, here's a 2, here's a 2, here's a 6. I would add these two equations together to write what I would refer to as the net redox reaction, or the overall redox reaction. We're going to use this overall redox reaction in stoichiometry. So that's why we have to figure this thing out. So on my reactant side, I should have 3 of the Fe plus 2 plus 2 of the Al0. Notice that I have 6 electrons on the reactant side, but I also have 6 electrons on the product side. The 2 cancel each other out. A net redox reaction no longer addresses the electrons. And just like with my previous 2 equations, the charges on each side of the arrow should balance out, along with the number of each atom. So I have 3 irons, 2 aluminums, 2 aluminums. I have a plus 6 on this side. I have a plus 6 on the other side. You have questions on that at all? Can I do another one? Let's do the next one. Sodium reacts with magnesium sulfate in a single displacement reaction. Sodium's Na. Reacts with magnesium sulfate. If it's single displacement, sodium sulfate will form. And so will solid magnesium. I'm going to ignore sulfate when it comes to oxidation numbers. So I got a 0 for the sodium, plus 2 for the magnesium, plus 1 for the sodium, and a 0 for the magnesium. Which element was oxidized? What had its oxidation number increase? The sodium. I could put a 1 in front of the E. But it's assumed to be 1. So sodium metal loses 1 electron. It becomes sodium plus 1. That means the thing being reduced must be magnesium. Going to go from +2 to 0. You don't have to write those zeros up above, but I typically do with redox to keep track of all these different charges. Plus they'll gain 2 electrons. What do we have to do to balance these things out? Got to balance the electrons gained and lost. Yeah, the oxidation equation needs to be multiplied by 2, and then we can put them together. We're going to do the last one as well. So we might as well fill out this entire sheet, then give you a little bit of time to work on doing this style. So the last question says hydrochloric acid reacts with lead. Now it says lead 2, but lead would be neutral to start with. It's trying to indicate what would the lead be when it became a compound. I notice that it's very common that single displacement reactions are involved with redox. It's not a must, but it is very common. Remember, the lead will replace the hydrogen. Hydrogen's a diatomic on the product side. Hydrogen is a +1 here. Again, chlorine is going to be a spectator ion, but I'll fill in that -1. Lead's a 0 on the reactant side, a +2 on the product side. Which element was oxidized? Is it the H+ or the Pb0? Which, by the way, that's one of the things that you're going to see on WebAssign is it's going to ask you what was oxidized. Reactants are the things that are oxidized or reduced. So you're not going to point to the product formula when you do that. And I'm also saying is that the H+1 that's oxidized, because that is the thing that could gain or lose electrons, not the H2 that's on the other side. So which one was oxidized? The Pb0, right? To be oxidized means you lose electrons. So I put the electrons on the product side along with the new charge of the lead. That would be my oxidation equation. Now, we do need to start to add a little bit to this, and that's why I wanted to make sure to get to this third problem. The H+ is what is reduced. However, when we on the product side write down what the H+ turns into, we have to keep it as a diatomic. And I'm going to expand upon this with the second half of class today, but I can't just write H, I have to write H2. And I can write the 0 on there if that helps out. So what I want you to keep your eye out for in this first practice round is diatomics. We have to write it as such, which means this is not balanced right now. I have to balance my number of atoms before I balance charges. So I have to put a 2 in front of my H+. Once you balance your number of atoms on the left and the right-hand side, now you can balance the charges as well, which means I need to put a 2 in front of my electrons here. Because now it's neutral on both sides. Lucky for us, the net on this one cancels out nice because I have 2 electrons here already. Add the 2 equations together. Pb plus the 2H plus. Doesn't matter what order you put the lead and the hydrogen ion in. Just remember that hydrogen ion represents it's an acid, which HCl is an acid.